flow control is the problem ensuring that the receiver has the capacity to receive your packet so that the sender does not flood. Suppose I want to get a file, and if I'm a little computer and somebody sends me 2 million bytes suddenly, or maybe 200 packets, I may not have the capacity to receive all of that. So we need a flow control. So we have to basically, the way we do flow control is that for every packet, the sender has to ask the receiver whether it can send the next packet. So simplest way would be the sender sends the one packet, receiver says, okay, I got one, now please send me two. Then the receiver sends two, and then the acknowledgement is sent, and so on and so forth. This way there is no overflow. However, the problem is that we are not using all the time. The sender is not always busy, the receiver is not always busy, so we are wasting a lot of time. It might take very long to send a long file. So one is not a good number to send, one packet. So we say, okay, all right, what if we can send 3 packets? So we can send 3 packets, 3 acknowledgement comes back. When the one acknowledgement comes back, we can send one more. When the second comes back, we can send one more. When the third comes back, we can send 3 more, one more. So anyway, so at any time there are 3 packets in flight. So one thing that transport protocols do or may do is flow control. And flow control is simply end-to-end problem. You just want to make sure that the receiver is not over-flooded. This receiver wants to control how many packets you can send to it, otherwise it will be over-flooded, it will have to drop it after the packet has reached the receiver. And that is called flow control. So receiver can limit the number of packets. For example, it can say, please send me 1 packet at a time. So you send a packet, you get the acknowledgement, then you send the second packet, you get the acknowledgement, you send the packet, you get the acknowledgement. This is called stop and wait flow control. If L is the distance, L is the length of the packet, L is the length of the packet, R is the rate, it will take L upon R, this much, this width of this thick line, L upon R time to put the packet on the wire, and then it will take 1 round trip delay before you can put that next packet on the wire. So in this much time, which is RTT, round trip time, plus L upon R, in this much time, only thing you are able to use is L upon R. So the efficiency is, our throughput is L upon R divided by RTT plus L upon R. As an example, suppose you have a 1000-bit packet and you are sending 1000 bits per second. What is L upon R? 1, right. 1 second. So this thick line is 1 second wide. Suppose the round trip delay is 5 seconds. And your throughput is 1/6. Good. All right. So this is not very good. I mean, you paid for a gigabit, but you are getting only 1/6 of a gigabit, which is not good. So what you do is you say, well, I want to send many packets at a time. So let's say in this case, the receiver allowed you to send 3 packets. So you send first packet and you don't wait for the acknowledgement. You send the second packet and then you don't wait for the acknowledgement. You send the third packet. Now you have to wait, because the receiver said you cannot send any more than 3 packets. You sent 3 packets, now you're waiting. When the first acknowledgement comes back, you can send 1 more packet. When the second acknowledgement comes back, you can send 1 more packet. When the third acknowledgement comes back, you can send 1 more packet, and so on. Right? In this case, how many packets you have sent in how much time? So let's say in this case, if W is your window, then you have sent W times L upon R. This is the transmission delay. This much time you have used, but total time is 1 round trip plus 1 L upon R. So your throughput is W times bigger. Yeah.
What is W? The number of
W is the window. Yeah, okay. So we call, okay, that's a good question. W is the number of packets that you are allowed, and we call it a window. So in this example, the window is 3.
Is it the max number of packets allowed?
So the receiver says maximum you can send me 3 before you receive the acknowledgement. So I mean you can send 200 packets by this method, but after 3 packets you have to stop until you get the acknowledgement. Once you get the acknowledgement, you can send again. So this is the maximum number of what we call outstanding packets. Outstanding means unacknowledged. Alright, so window flow control is good because now depending upon what your window size is, your throughput can go up. Obviously it cannot be more than 100%, but you can use all the way up to 100% depending upon the window. And you can calculate the window from here too as to what the window is required. Yeah. Alright, so the question is, what is this throughput? This should be bits per second, but this is not bits per second. This is actually percentage. So this one, for example, this comes out 0.5. That doesn't mean 0.5 packets per second. This means 50% of your capacity. So if this link was a gigabit, then 50% of the capacity is 500 megabits per second. So this is actually somewhat, we should call it normalized throughput. This is only between 0 and 1. This cannot be less than 0, it cannot be more than 1, and so this is basically percentage throughput, or the fractional throughput. Right? It is dimensionless. This is in seconds and this is in seconds. Seconds upon seconds is no dimension. So this is basically normalized throughput. We also call it efficiency. Efficiency is same as this one, which is normalized throughput. So right now it is not bits per second. It is just the efficiency. It tells you 50% efficient or 20% efficient. And this is called sliding window flow control because if suppose the window is 5, each packet has a number on it. When you send a packet, you put a number on it, and the numbers could be, for example, 0, 1, 2, 3, 4, 5, 6, 7, and then 0 again. Because the numbers have only so many bits. So suppose you reserve 3 bits per number in the packet. So if there are only 3 bits for the number field, then the number would be 0, 1, 2, 3, 4, 5, 6, 7, and then there is no way to express 8. 8 becomes 0. Everybody understands that? With 3 bits, the maximum number could be 7. Alright. So the numbers are 0, 1, 2, 3, 7, then 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. And every time a packet, so basically suppose the receiver wants 5 packets outstanding. It wants to use a window of 5. So as soon as basically, so now let's see what happens. We have sent 7. Right? If we send the next packet which is 0, then the window goes down by 1. If the next packet is acknowledged, then this edge goes up. So this edge goes up when the packet is acknowledged. This edge goes up as the packet is sent. And this is the window that can be sent. So the receiver says you can send up to packet number 4, but we have sent only up to 7, so we can send 0, 1, 2, and 3, and 4. So this is the window of the packets that can be transmitted. And this window keeps expanding and contracting depending upon how the receiver allows or how you transmit. And if you keep it in lockstep, this window keeps moving. In the sense that if you just wait for the acknowledgement, as soon as acknowledgement comes back, you send 1, then so this can keep moving. So this is called a sliding window. Sliding window. So here in this example, the window at this point is 3, then it is 2, then it is 1, then it is 0. Then the one acknowledgement comes back. Now the window has moved in terms of the number, sequence number, but the window is right now 0, then it becomes 1, and then 1, 1, 1, and then 0. So this basically remains 1, 0, 1, 0, 1, 0. The window doesn't really ever become more than 1. I mean the leftover thing, right? So anyway, so basically that is how it happens, is that every packet is numbered and there are only few bits allocated for the number, and so the sequence number simply wraps around to 0. And the second concept is that every time the acknowledgement comes back, you are allowed to send one more packet. Every time you send a packet, you are allowed to send one less packet. So the question was, why would you send 3 acknowledgements as shown here? Why can't you just send the last acknowledgement? Well, that is the optimization, because if you just send the last acknowledgement, then you won't be able to send these 2 packets early. You will have to wait until the last packet is acknowledged, and then you will send 3 together. That will cause a little bit more burstiness, but it will save some acknowledgement bits. But so the thing is, there is some positive, some negative there. All right. So the first thing was called stop and wait flow control. I gave you the formula before, but here it is again same formula one more time, just in little bit more zoom. So the first bit is transmitted and the last bit is transmitted. This is how long it takes to transmit the packet from 0 to L upon R. Then you have one round trip, assuming that the acknowledgement is very thin, doesn't have too many bits, then you're done. So the total time is RTT plus L upon R. Used time is L upon R, so that is the utilization or efficiency. This is also called T frame time, and this is called prop time. 2 times the prop time plus 2 times plus the T frame time. If you divide both the numerator and denominator by the T frame, this is 1 upon 2 alpha plus 1, where alpha is the ratio of prop to frame time. So U is equal to 1 upon 2 alpha plus 1. This is a very important formula, because alpha, which is the ratio of prop to frame, is very important parameter. And we will be using it quite a bit. And remember, this is always prop to frame. So prop is on the top and the frame is on the bottom. You calculate the ratio, and that alpha value will determine the efficiency of the protocol, and this is actually coming up in a minute again. So basically, right now you can remember it in one of these many ways. One way is to write like this, another way is to write like this, and third way is to write like that. Okay? Alright, all 3 are equal. But remember, alpha is prop to frame. Alright, then sliding window. In the sliding window now I have shown the frames back to back. So 3 frames, and then the last edge, bottom edge of the first frame causes an acknowledgement, and therefore the total time is 2 prop plus frame plus W times the frame. So if you were to divide by T frame, you get W upon 2 alpha plus 1. Obviously, it cannot be more than 1, so if W is greater than 2 alpha plus 1, all you get is 1. And if you put W equal to 1, then you get the same formula as before, which was 1 upon 2 alpha plus 1. So stop and window is a special case of, stop and wait is a special case of window flow control, where window is 1. So you don't have to remember 2 formula, you can just remember 1 formula, and then if you put W equal to 1, you get the previous formula. We can do some examples here just to understand. So let's say we have a satellite link. Alright, satellites are very far away, but they are used for internet and communication. The way it works is that you send the signal to the satellite, and then they send it back to the other part of the world. So if you want to go very far away, or you want to cover the part of the world where there is no other infrastructure, satellite is the best way to get there. So satellite link but takes a long time. So the light itself takes 270 milliseconds for one way, quarter of a second to get to the satellite. So round trip delay is 540 milliseconds. Now if you send a packet which is 500 bytes long, multiply this by 8 to get 4 kilobits. If your data rate is 56 kilobit per second, your frame time is 4 kilobit divided by 56 kilobits per second gives you 4 upon 56 seconds, which in millisecond is 71 milliseconds. So everybody can get that 71 millisecond, right? What is the length of the packet divided by what is the rate? So alpha p prop upon t frame is, now this is one way propagation relay. Remember, this is not round trip, so don't get confused here. T prop, one way propagation relay is 270 divided by frame time is 71, so the alpha is 3.8. Alpha is 3.8, then u is 1 upon 2 alpha plus 1 if it is stop and flow, stop and wait, then it is 0.12. U is utilization, efficiency, normalized throughput, whatever you want to call it. The utilization is 12%. 0.12 means 12%. If you paid for 56 kilobit, your throughput would be 56.1 times 0.12. So the acknowledgements are very thin, in the sense that acknowledgements might be 8 bits or 10 bits. So that is negligible. We are just neglecting that. Alright, now, so this is a very long link. On the other hand, let's take a short link. A short link, 1 kilometer fiber, will take 5 microseconds for the light to go. And this is something that generally most of us remember, that the light takes 5 microseconds per kilometer, 200 meters per microsecond. Now this is light in the fiber. In the air it takes 300 meters per microsecond. But in the fiber it is only 200 meters per microsecond. So 5 microsecond for 1 kilometer, and the link rate is 10 megabits per second. Suppose you have 500 byte frame, then the P frame is 400 kilobits divided by 10 megabits. So anytime we give you bytes, in the networking world we don't use bytes, we always use bits. All the rates in networking world are in bits. So when we say 56, it is bits. When we say 56 megabits, it's bits. Okay. When you go to the storage world, there they don't specify anything in bits. Everything is in bytes. Right. So don't get confused. Okay, little b and capital B. We use little b and capital B. So bytes is capital B and the bits is little b. If it is only written. Otherwise, if you write the whole word, then it doesn't matter. But if you don't write what is after B, then little is bit and capital is byte. Okay. Alright, so back to this. T frame is 400 microseconds. And T prop is only 5 microseconds, so use that formula, 1 upon 2 alpha. So alpha is actually 0.012. T prop upon T frame is 0.012 and utilization is 98%. So now you see you're getting 98% utilization, which is really good. You're not wasting any time, almost. So, how can you increase the efficiency here? Suppose you do have to use satellite link. What can you do to make it better? Can you look at something that you can change? Yeah, so on the longer links, you need to have bigger frames. That is the same message here. On the longer links, you need to have messages, frames bigger, that the alpha is small. Now, another interesting thing is that, what about the speed? If this was slow speed, let's say this example, let us take it here. This example was 10 megabits. So that's why it came out to 400 microseconds. But suppose it was 1 kilobit or something like that. Right? If it was 1 kilobit, then this time would be 4 kilobits upon by 1 kilobit would be 4 seconds. And alpha will be 5 microsecond divided by 4 seconds. So 5 upon 5 microsecond divided by 4 seconds. That is a very small number. And you would be, sorry, let me see. If the rate is high, if the rate is low, then T frame is large, and then so that's fine. Okay, so the efficiency is high. I was going to go other way around actually. If the rate is very high, let's say this was not 10 megabits, this was 10 gigabits. if it was 10 gigabit, this number would be a million times smaller, right? Or maybe 1,000 times. Yeah, 1,000 times smaller, right? And this number alpha would be 1,000 times bigger, because frame is on the bottom, and this number will be very small. So if you have a long link or you have very high speed link, the efficiency is low. To improve the efficiency on either the long link or on the very high speed link, either case you should use big packets. So either because you are going to satellites or because you are going to very high speed links like 10 gigabit Ethernet, you should use big packets.
So will TCP automatically set packets based off of some parameters for you or something?
No, it doesn't. It doesn't. It just, so the thing is, TCP doesn't really know the speed of the link, and then there is not one link, there are many links. These formulas that we are talking about is actually, although they are true for many links, but the calculation that we did here is just for one link. And so when you go, you might go through some low speed, some high speed, some long distance, some short distance. So it's the overall rate that we are talking about here and the overall frame size, but TCP actually doesn't explicitly know this, but you as a user know it. So you can ask TCP to use certain windows, otherwise it will just find it out by experimentation. So here's a graph. Actually, by the way, before I go further, the textbook does not use this kind of formula. The textbook uses RTT in place of T prop and L upon R in place of T frame, and I am going to use it because this is very powerful conclusion which I am going to, and I have want to emphasize that will come back soon later on. So it's very important to understand alpha. The textbook does not use even alpha. But in computer networking, one of the fundamental principles is that the efficiency always goes down for every protocol if alpha goes up. And therefore, you should always try to keep alpha small. Large alpha is bad for every protocol, not just for this window flow control, for error control, for anything we talk about. And that is very powerful thing to know. And therefore, using alpha, using T prop, T frame is better. All right. So as the alpha goes up, if you plot for various values of alpha, for various values of windows, and here it says N rather than W, because this is not from the book, this is from another book. But basically the idea is, for a given window, 1 means this is stop and wait, 7 means the window of 7, and 127 and so on and so forth. As you increase the window, the total utilization goes up. So if you had alpha equal to 1, with n equal to 1 you will get this much, but with n equal to 7 you will get that much, and so on and so forth, right? But as alpha goes up, for every protocol, in this case, the efficiency goes down. This curve can never go up. So larger window is better. So here, if you do have large alpha, then you should use as large a window as you can, basically. So if your alpha is 100, you want to use 127 or something. So this is the principle which I have already told you, but this is a general principle, and it's not in the book, but it is very powerful, and I want to make sure everybody just memorizes this. For all protocols, and this is where it is, there are no exceptions. For all protocols, the maximum utilization efficiency is a non-increasing function of alpha. This is also mathematically correct, non-increasing. Non-increasing means the best thing you can do is not increase, remain constant. But this is not possible. All it is possible is mostly it will go down. And different protocols will be compared based upon how fast they go down. Some protocols will go down very fast, some will go down slowly, the best you can do is remain the same. Alright, so the principle is, for all protocols, the maximum utilization or efficiency is a non-increasing function of alpha, where alpha is t prop upon t frame. T prop is equal to distance divided by the speed of the signal, that is the propagation delay. T frame is the bit transmitted divided by the bit rate, right? And if you bring this up and down, you get distance times bit divided by the bit transmitted times the speed of signal. Alright, now this is important because alpha is this. So large alpha means large what? What can be large? Distance can be large, bit rate can be large. If either of the two cases, if you have a very high speed link or if you have a very long link, alpha can be large. Another reason alpha can be large is if you don't transmit enough bits on that one. If your bit transmitted is small, right? And the speed of the signal is not much you can do about that one. Alright, that is kind of given to you. So we play with these three things so far. I mean, we could play someday with that too, but right now we have three controls. So this is why we call it distance bandwidth product. This is that, distance bandwidth product. Whenever you have a large distance bandwidth product, you have large alpha. It doesn't matter whether the distance is large or the bandwidth is large. It's the product that matters. And whenever the product is large, you have to use large packets. You have to do something, about that, because otherwise the efficiency will be very low. All right. So that is not in the book. Please remember that one. I just think that is very important message, and this is the right point to give that message. And basically, it's the alpha. All right. So now we finished the flow control. Actually, believe it or not, but basically, we talked about two different methods of flow control. One was called the sliding window, and one was called stop and wait. And stop and wait actually is simply W equal to 1. Basically, window is the number of packets that can be outstanding without acknowledgement, and the larger window is better for efficiency reasons, and it affects the efficiency. And here is the formula: W upon 2 alpha plus 1. Okay. Never. So basically, the reason you will use stop and wait is because okay, there are some cases where stop and wait might be okay, and that is that you want to keep life simple. For some reason you don't want to write very complicated protocols or complicated code. That is one thing. Second thing is, if there is a lot of errors, if the error rate is very high, then you don't want to have 2,000 packets outstanding and then you have to retransmit lots of packets again and again. So you just send one, and if it doesn't make it, you send it again, and you send it again, you send it again until it makes it. But most often we just use window, which is more than one.